Hello, everyone. Our second speaker, Johanna Ulvedal Marstrander. She's a PhD student from Norwegian University of Science and Technology. Her talk today is numerical analysis of Fourier spectral method for the system modeling water waves. Please go ahead.
Hi everyone, I'm Johanna. I'm very happy to be here. Thank you for letting me speak and for listening to me. As you said, I will be presenting some numerical analysis of a Fourier spectral method for systems modeling water waves, and my background is in partial differential equations modeling water waves. And this talk is based on an ongoing project with Vincent Duchenne at the University of Rennes in France, but it's yeah, there is no paper yet, but it's coming. So yes. Okay, so first I will just say a little bit about the kind of equations that we look at and that we want to study simulations of. So the water wave problem is really usually described by the Euler equations, and then you have boundary conditions and initial conditions, and this gives kind of the water waves problem. But the equations that I am studying are more simplified model equations for this problem. So the situation that we have is typically what I've shown a picture of here. There is a body of water that is restricted by a bottom, which is in this case flat, and by the free surface. So the problem with water waves is usually that we don't actually know what domain we're looking at, this because the surface is free, and that is part of the problem, is finding the surface. So we will have two unknowns. One is the surface profile, and the other is a velocity. So this can vary from equation to equation what this velocity really is, but you can think of it as like a horizontal velocity, for example, a vertically averaged velocity. And so these equations, to find these simplified model equations, what you usually do is that you will have some characteristic sizes in your system. So there will actually be a depth, there will be a wavelength, there will be an amplitude, and then you will assume that some of them are small or large and do an expansion and then neglect a bunch of terms, essentially. And then you get a simpler equation. And these are the kind of equations that I look at. So additionally, in this particular talk, I will just consider one horizontal spatial dimension. There is no good reason for that. Everything carries over to 2D, but it makes everything easier to present. And then water waves are usually studied in one of two contexts. Either it's sort of on the whole real line, so you have an infinite amount of water, and at infinity it's at rest. Or you study periodic solutions, which is natural because, well, waves are quite often periodic, right? So I will stick to the periodic case in this talk. And sort of one of the most basic or simplest nonlinear systems that you get is the nonlinear shallow water or Saint-Venant system of equations, and it looks like this. I don't know, can you actually see my mouse sort of moving around? Okay, then I shouldn't move it so much. Okay, but you get something like this, right? But if you want something more exact, a more exact model, then there are different ways to get that. But one class of sort of slightly better models is of exactly the same structure, but then additionally, you have added operators to a bunch of the terms. And these can be simple operators or more complicated operators. And in this water waves world, we like to formulate these operators as Fourier multipliers. And Fourier multipliers, they are pseudo-differential operators that are defined through how they act on sort of the Fourier transform of the function. So in the periodic setting, you can say that the action of the operator m on the function u is just defined by you take the Fourier series of u, and then you multiply each properties of water waves. Okay, so this is the kind of system that we want to consider. And the ultimate goal, I guess, in this presentation is to look at how exact numerical simulations using Fourier spectral methods are. Okay, so the method, the Fourier spectral method, is it works like this, essentially. When you do a numerical approximation, you want to reduce the continuous full problem to a finite dimensional problem that you can actually solve. And what we do here is that we approximate all the functions by finite Fourier sums. So you take the Fourier series and you have time-dependent coefficients, but you sort of truncate it after n terms. So you don't have an infinite Fourier series, you just have the first n terms. And then you look for solutions like this, finite Fourier sums, to exactly the same systems that we had earlier, but you look for only these finite Fourier sums. And then in addition, you need to apply a projection operators on the nonlinear term. And the reason for this is that we will pick initial data that is a finite Fourier sum, but we want to ensure that we continue having finite Fourier sums as the equation evolves. So for the linear terms, this is automatic, but for the nonlinear terms, it is not automatic, because if you take two finite Fourier sums and multiply them, you will sort of get a higher order exponential function. If you take e to the power I n x and multiply it with another e to the power I n x, then you get 2n up here. And this is not allowed because we only want those with lower power than n. And so to all the nonlinear terms, we apply this projection operator, which is essentially just that if you apply this projection operator to V, it means that you take the Fourier series of V, but you chop off all the high frequencies. Okay. The good thing about this system, there's a lot of the same here on this slide. So the good thing is that this projection operator can be written as a Fourier multiplier as well, which means that you can pick a good function here and just write this operator as multiplication of the Fourier transform with some function. So you take the full Fourier series and then you multiply it with the characteristic function, which is 1 for all the coefficients smaller than n and 0 outside. And so you can write this as a Fourier multiplier, and you can formulate the spatial discretization in exactly the same way as the original equation. And so when we want to show things like stability for this equation, we can basically mimic exactly the strategy that has already been used for the underlying system. And another advantage of this is that when we want to implement it, what we do is that we take the Fourier transform of the whole system, and then we get a system of ODEs for the Fourier coefficients. And here, all the differential operators, like differentiation here, and these operators they just turn into multiplication by something with the Fourier coefficients. And this means that if you take more difficult operators, then essentially nothing changes in the implementation. So it is really, for this class of equations, a very natural choice of a numerical scheme. Okay. So what we will actually show, we will do in a slightly more general context. So we will consider a fairly general quasi-linear system of equations. So we now put our unknowns eta and u into a vector, and we have this system where A of u is a matrix which depends smoothly on u. And this is now our equation, and it has some sort of initial data. So this is a continuous underlying system, and we know that this is well posed. Okay, and it also covers the equations that I've talked about already. If you just write it in a new way, then you see it sort of goes directly into this formulation.
Quick question, is this only R2 or can you do sort of more general?
If it's only what?
Are you only talking about R2 or Rn? Like your capital U, like it has two components.
No. So I'm doing so now. No. You can easily generalize it to higher, both to more spatial dimensions and more unknowns here. Yeah, nothing changes really. Okay. But then in this formulation, the spatial discretization is as before. We just looked for finite Fourier sums instead. And then we need to apply this projection operator to the nonlinear terms. And except for that, nothing changes. And for the initial data, we just also apply a projection operator to the same initial data. And the ultimate goal is then to show that, well, that this has a solution and that we can bound the difference between the U, the solution to the continuous system, and the numerical solution UN, and that we get a bound like this, where S here is a parameter that says something about, is related to the initial data. So yes, I will say more about this on the next slide. So I will try to keep sort of we'll see. Okay. So we consider functions. We have to estimate the error somehow, right? And we will estimate it in the L2 norm. But how good our estimates are will depend on how smooth the initial data is. So we also consider the Sobolev space HS, which are L2 functions with a bounded HS norm. And essentially, the HS norm is functions that are bounded in L2 and whose derivative number S is also bounded in L2. And the good thing, if we write the norm like this, which is essentially the same as what I have here, the good thing is then that it's very easy to show that the difference between a function and its projection is given exactly by this. So if we have a function which has a high regularity, then the Fourier coefficients will decay very quickly, and the difference between the projection and the function itself is very small. And that's why we also expect spectral convergence for this kind of schemes, because we expect that the solution that we eventually get is kind of close to just the projection of the solution itself. Okay. Yes. So I will not say a lot about earlier results, except that there are not that many earlier results. They are either for specific equations or they are sort of, there are a lot of numerical results, but not that many proofs. And so we wanted to do a bit more general things than what has been done before. And these are the three that are sort of closest to what we have done, but they are either for specific equations, as we can see here, or they have suboptimal convergence rates. Yeah. Okay. So we have the continuous problem and we have the semi-discrete problem, and we want ultimately to show that the difference between them is small, and it's smaller the higher n is, and also the more regular the solution to the original equation is. And the strategy to do this is first to show that there is actually a solution to the numerical scheme, to this problem here, to the semi-discrete system. And this is very easy because it is a finite dimensional problem. And so a local existence of a solution for some time interval just follows automatically from Pickard iteration or Cauchy-Lipschitz theorem or just standard theory. But then we want to show that it is bounded, and this bound is independent of n, and that it at least exists for like a minimal time, which is also independent of n. And to do this, the key element is an a priori estimate, like we have here. So first, we need to show an a priori estimate like this, where we have the time derivative of the norm in HS of the solution, where this is bounded by the HS norm of the solution itself. And from this, we can use Grenville inequality to get an estimate like this. And then the thing with the existence time being independent of n, this is a standard continuity argument, which I won't talk about. And then once we have these estimates for the numerical solution, then we can go ahead and compare the continuous and the numerical solution, which we do simply by subtracting the two equations and then doing essentially the same thing to get the next estimate, but now for the difference. And then finally, we want to show that this actually holds not only for some time t, but actually as long as the underlying system is well posed.
So quick question again. So
yeah.
So in point 3, I assume the c depends on your existence time, right? So I mean, it's not uniform in t. Yeah.
And yes, it depends on the existence time. Yeah. Yeah. That's true.
You use the ground law inequality, so you also have the exponential of the time, right? Exponential.
Yes.
Okay, thanks.
Yeah, yeah, that's true as well. Yeah. Okay. But the key here is finding this estimate. I think this is sort of what I'll spend some time talking about. Okay, so in the interest of time, I think, because I started a little bit late, I think, and I have too much to say, I think I will skip most of this slide actually. But what we want to have is an estimate like this that I have at the bottom. We want the time derivative of the HS norm bounded by the HS norm itself. So for the L2 norm, what we do is we write this. This is just can be rewritten using the L2 inner product, and it's the same as this. And then we just use the equation here. But then the problem, if we want to estimate this using Cauchy-Schwarz inequality or something like that, is that we have too many derivatives on the u. So what we need to do is that we need to be able to shift things around and move this derivative around to get it in the right spot so that we don't have one too many derivatives on the u's. And the key ingredient to do this is commutator estimates. So if you've sort of done this thing before, then you already know this. And otherwise, I don't think I have sort of enough time to explain it properly. We need commutator estimates to be able to shift things around and get the derivatives where we want them to be. And the commutator estimates are essentially like this. So here I've written down the commutator just for the derivative and a function. And what this means, just the notation is that first you apply it to the product of g and f, and then you put g outside and just apply it to f. And the result is that in the end, the operator is not applied to the function which is in the back here. So while here you have a first order operator, in the end you have nothing or just a zeroth order operator applied to the f. So you lose one derivative on one of the functions. And that's very nice because, as I said, we want one less derivative here. So the key are these commutator estimates. And they hold for a lot of nice operators, but they need to have some regularity for these commutator estimates to sort of be true. And the problem with the numerical scheme that I've presented so far is that commutator estimates such as this, they do not hold for this projection operator. So this projection operator is, of course, very nice. It's a projection. You just have a very nice characteristic function. But if you see at what happens here, what you actually multiply with on the Fourier side, then this is a sharp cutoff function. It is not Lipschitz. And it's not nice enough for these estimates to be true. So the initial idea was to replace this very sharp cutoff with a smooth version of such a cutoff function, like this. So where you still put all the high frequency components to 0, but where you do it in a smooth way. And then for this kind of operators, then all the commutator estimates work. And so what we expected was that if we replace our sharp cutoff with this smooth version, then everything would work in the numerics. And we also expected that if we take the sharp cutoff, then we would be able to show that something blows up, that it actually doesn't work in some specific cases. And we did show that, well, for the smooth version, everything works, but it turns out that most of the time it also works for this sharp cutoff, and so we wanted to understand why. So for symmetric systems, if this A operator is symmetric, then it's very easy. If you look at the semi-discrete system instead, then you have the L2 norm, time derivative of the L2 norm. It is equal to this. By the equation, it is equal to this because the time derivative is equal to this part here. And then by orthogonality, this is just equal to this. The pi just disappears because of orthogonality. And so you're sort of back to exactly the same situation that you had with in the continuous underlying system. And everything is exactly the same, and you get exactly the same estimates as it does in the continuous system, and the projection operator doesn't matter at all. And so everything works out. But the problem is for symmetrizable systems. So when AU is not symmetric, then you need to apply a symmetrizer to your system to be able to get estimates. So a symmetrizer is an operator which is symmetric and positive definite, and which is constructed in such a way that when you take the product with A, you get a new symmetric operator. So you want this thing here to be symmetric because then you're back to the symmetric case, basically. But then you also get this on the left side of the equation. Yes, but that's okay because you can rewrite it. And now instead of getting an estimate for the HS norm, you get the estimate for an energy. But that's okay because your SU is positive definite. And so in the end, you still get an estimate for the HS norm. So this is what you do in the continuous case for a symmetrizable system, which is not symmetric. Now, for the semi-discrete system, we can take the same symmetrizer as for the continuous system. But the problem now is that we have this projection operator in the middle, and this combination here with S and then the pi operator and then A, this is not symmetric in general, even if this was symmetric. And it's very easy to see. So it just doesn't work with any symmetrizer in the analysis. If you instead take the smooth symmetrizer here, then you're still good because you can move it around and get commutator estimates. So instead of having it in the middle, you can put it inside and get an additional term with the commutator estimate, but this is fine because this is a very nice and smooth operator. Yeah, okay, so yes, and after you have your estimates, you can compare the solutions, and it's not completely straightforward, but I don't think I have the time to go into these details either. You can ask if you want. But just summarize shortly, what we get is that for symmetric systems, we can show that the spatial discretization is well posed, and we get exactly the bound that we want. And we get these results with both the sharp cutoff and a smooth version of the cutoff function. For symmetrizable systems, we need, or what we have been able to show is that it works if we have a smooth cutoff function instead of a sharp one. And then we also get the estimates that we want. Now, the problem, we are not completely happy yet because we could still not construct any example of it not working numerically. It always works numerically, even if you sort of do everything you can to make it go super wrong in all the estimates here, it still works numerically. So we're trying to figure out what happens, even if you take the sharp cutoff function here. And so we have some preliminary results, but I'm not completely done here. And the thing is that for a symmetrizable system, a general symmetrizer, any symmetrizer won't work. But there is always one symmetrizer that does work for a Hamiltonian system. So if the system has a Hamiltonian structure, which it often does in the water waves systems that we are considering, then we know that from just general theory, the Hessian of the Hamiltonian energy is always a symmetrizer. And then you can modify the Hamiltonian energy, and you can do it in the same way every time. And this will give you exactly the spatial discretization. And of course, now you have a Hamiltonian energy for a Hamiltonian system, which is the spatial discretization. And so you know that the Hessian is a symmetrizer. And so we can actually show that we have convergence also for symmetrizable systems when we have this sharp cutoff. But the problem is that this only works for one symmetrizer in particular, and this gives like additional restrictions that does not seem to would fit with what we observe numerically. Yeah. So yeah, thank you for listening. I think I'll stop there. Yeah, these are some pictures of from my office in the main building in Norway, and this is, I just wanted to show because it's been insane with snow lately. This is what it looks like right now. So thank you again for having me.